As promised, next video here, radiative balance. So we get the most energy from the sun in the northern hemisphere on June 21st. Why are we not the warmest then? Well, this concept of radiative balance is the reason why. So let's figure out what this means. The Earth's surface temperatures depend on a balance between the energy we get from the sun as insolation and the energy we lose back to space by the Earth's surface re-radiation. We get radiation and we give it back off, so it's re-radiation. It's really, since it's the Earth, it's a big topic, but it's almost the same as your house. The temperature inside your house depends on how much energy your heat source puts out and how much energy your house loses back to the air outside. And the Earth works the same way. There's got to be some sort of a balance there. And that's what we're talking about. So the highest and lowest temperatures do not come at the same time as the maximum and minimum insolation. And there's a good reason for that. Anytime your incoming energy, your incoming solar radiation is greater than the amount of energy you're losing or re-radiating, that is going to cause you to have a surplus of energy. If you're getting more than you're losing, you have a surplus. If there's a surplus of energy, that causes the temperatures to rise. Again, your house is the same way. If you have more energy being given off inside your house than you are losing to the outside world, the temperature in your home would go up. The Earth works the exact same way. If you're getting more than you're losing, you have a surplus, so the temperatures rise. If the opposite is true, if insolation, incoming energy, is less than re-radiation, how much we lose, then we have an energy deficit, a shortage of it. That's going to cause the temperatures to fall. It's really pretty logical. There's a lot of big words, irradiation, deficit, surplus, insolation. I get that. But, if you're getting more than you're losing, the temperatures go up. If you're losing more than you're getting, the temperatures go down. It's a pretty straightforward concept. So, here's the deal. Maximum and minimum temperatures occur at shifts between surplus and deficit. At this time, incoming and outgoing energy are equal. When they're equal, it's said we're in radiative balance. It's an equilibrium where energy in and energy out are the same. So graphically, this I think makes a lot of sense. So if we take the 4 key days of the year, December 21st, March 21st, June 21st, September 23rd are 4 key dates. If we were to graph the incoming solar radiation at a particular spot, this is what we'd have. Don't worry about numbers and units and all that. This is going to be a minimum on December 21st for energy from the sun, going to be a maximum on June 21st for energy from the sun, and it just constantly increases throughout the winter and spring, reaches a maximum at the first day of summer, and then it steadily decreases back until December 21st. Now, if we look at how much energy the Earth loses, see, sunlight comes in, warms up the ground keeps getting warmer and warmer and warmer, so it's going to radiate energy. It looks like the same line, it's just shifted a little bit. This is what we see when we measure these values. And so anytime your incoming energy is greater than your outgoing energy, if insolation is greater than ground radiation or re-radiation, you'll see it in questions as, then we have a surplus. If we have a surplus of energy, we just said on the previous slide, what happens? Hopefully you answered that, or it was really awkward right then. If you have a surplus of energy, the temperature is going to go up. So all from this crossing point until this crossing point, we have a surplus. So that means our temperatures should steadily be increasing. All right. Now, once they cross, now outgoing energy is greater than incoming energy, and we have a deficit, and that comes back over here into the winter months. So then we have a shortage that's going to cause our temperatures to fall. So now if we put our temperatures on here, our minimum temperature is going to happen when these two lines cross, because that's the end of our deficit, our shortage of energy. And it looks like it happens December, January. So we're like just into February. That's going to be our time of minimum temperature for the year, typically. Again, day to day, year to year, there's going to be changes, but overall long-term average we're talking. Maximum temperatures occur over on this side of it, not on June 21st. On June 21st, we do have a lot of energy coming in. What we do on June 27th and July 4th and lots of other days too, more than we're losing, so the temperatures keep going up. Our maximum temperature happens, it's about 6 weeks after the summer solstice, when we have radiative balance again. So if I put the temperature graph on there, this is what we have. Minimum happens about 6 weeks after December 21st, puts you at the beginning of February typically. And the maximum temperature happens at radiative balance about 6 weeks after. That puts us at the end of July, the beginning of August is when it's typically the hottest. This graph will be provided on the classroom page to add to your notes. So during the year, highest and lowest temperatures happen approximately 6 weeks after the maximum and minimum insolation. It's not set in stone, like it's a law, it has to be 6 weeks, but it's approximately that. That's a good number to remember. That's when radiative balance is going to happen. So we're going to either stop having a surplus or stop having a deficit. We're going to stop increasing our temperature or decreasing. Now that's the long-term, whole year thing. This happens every day also, because we have this cycle of the sun going up and the sun going down, and that's going to influence how much energy we're getting. During the day, we have a maximum amount of insolation happening at solar noon, but it's not usually hottest at solar noon. It's hottest sometime mid-afternoon, maybe 3 o'clock or so, approximately. That happens, again, we're still doing the radiative balance concept. It happens when radiative balance is reached, because from noon until when we're the hottest, we still have a surplus. We have extra energy, more coming in than we have going out. So that makes our temperatures rise. The lowest temperatures are going to happen just a little bit after sunrise, because even once the sun comes up, it's such a low angle that we don't get a lot of energy from it. Yes, you can see, which is great, but we're not getting enough energy coming in to overcome what we're losing still. So it's pretty close to sunrise. Maybe within the first hour after sunrise, you're going to have your lowest temperatures typically. So if we do the graph thing again, and this is for a kind of typical, more summer-ish kind of day. Maximum is going to be at solar noon for energy coming in. Minimum is all night long so sunrise, we stop our 0. Sunset, we go back to 0. We graph ground radiation. It looks a little different on a daily basis. It's not exactly like on the other one where it was pretty parallel. But the surplus is still going to be when incoming energy is greater than outgoing energy. So from shortly after sunrise to middle of the afternoon, we have a surplus. Now, when we have a big surplus, like in here, and from solar noon, right around solar noon, we have a big surplus there. That means the temperatures are going to be going up pretty quickly. As the afternoon progresses, the surplus gets smaller and smaller. So our temperatures are not going to continue skyrocketing upward. They're going to very gradually peak out and then start to fall. So the bigger the surplus, the faster the change is. And the same is true with deficit. So we have a deficit from the middle of the afternoon all the way until shortly after the sunrise the next day. So our temperature should be falling. Now, again, this is average. Weather systems can go through and totally mess with us on a daily basis, but this is just saying, ignoring the weird weather coming from odd directions, this is what we should see. So we have radiative balance here a little bit after sunrise. That's when we're going to be at our minimum for the day. And we have another radiative balance point over to the right, sometime between 2 and 4 in the afternoon. That's when you're going to reach your maximum temperature for the day at the point of radiative balance. It's a super important concept. I've said it 50 times and I'll probably say it 50 more. So please try and remember this. You will see it again. And we could throw the graph for temperature on there. Minimum temperature, maximum temperature. So you'll have these that you can refer to. Now, on average, over a long period of time, the Earth is in radiative balance. We're pretty consistent temperature-wise. Now, things have been going on with pollution and human influence to this, where we have in the last 100+ years definitely seen an increase in temperature. Talk about that probably more tomorrow. But overall, we're pretty consistent, which is why we get concerned when we don't stay pretty consistent. So average temperatures remain constant when the Earth is in radiative balance over a long period of time. If the Earth is not in radiative balance, then you're either going to see temperatures go up or you're going to see them go down. And both of which have happened in the past. We have evidence from this from ice cores that we can look at, and from sediments in the bottom of ponds we can analyze. It's a thing. Now, one of the more notable ones is sort of the opposite of where we're going these days. If you have a long period of time where incoming energy is less than outgoing energy, that's going to cause the average temperatures to drop. And you can end up with an ice age. In the last million or so years, there have been 3, 4, maybe 5 different ice ages. There's been several times where the Earth's temperature has dropped, and that certainly has influenced life on Earth and other processes not involving life on Earth too. But an ice age is when we lose more than we gain. Ice ages are really tricky because once you get into them, it's hard to get out of them because snow, and we're going to talk more about this in the next video, but snow likes to reflect light, obviously. And so if you have a more snow-covered surface, more energy is going to be bounced off it, and that makes it harder for the temperatures to go up. So ice ages can last a long period of time. We're not talking about like one cold winter. Ice ages can last thousands of years, but we'll come back to that. So for today, the key term that you really have to understand is radiative balance. Look back at those graphs, and of course, I'll have a worksheet waiting for you. Thanks for watching.